This is part 5 of the Module 11 lecture. In this section, we're going to talk about the coefficient of determination r squared. So this coefficient of determination, or r squared, it measures how well the independent variable x describes the dependent variable y. In more general terms, we say that r squared is a measure of how well the model fits or describes the observed data. That's another way of restating this first statement. Also, the r squared is a proportion of the total variability in the data that is explained by the regression model. Let's see how we can determine r squared. All right, to understand and calculate r squared, it's important to do what is called the decomposition of the overall deviation of a value, of an observed value y from the mean. And I'm trying to show in this graphically here. So here's a particular observed value y for some value of x. And then there is a regression line, the sample regression line. And there is a value that we predict using that regression equation for x sub I. All right, so with that information, we say that the deviation of an observation from the mean of all the y values, so y sub I minus y bar, can be broken into two parts. The deviation of the predicted value from the model, from the mean, and that's how much deviation, we said that's how much deviation the model explains. And there is a portion that is not explained by the model, and that's the residual. In other words, the deviation of the observed value from the predicted value. So you see these two quantities add to this quantity. And this is the decomposition for a single x value, for a single observed value, for a single x value. So what we do is we take these deviations of each value, we square them and sum them to form sum squares. Let's look at what these sum squares are. So the first one is what is called the total sum squares, or SST. The total sum of squares is obtained by squaring the deviations between the observed value and the mean. So for each x value, we take these deviations, we square them and sum them over all the deviations that we have. And that's what we call the total sum of squares, and let's use the SSYY. This total sum of square represents the total deviation of the observations from the mean of all the observations, y bar. Now, if you notice, if y does not depend on x, then the regression line will have a slope of 0. In other words, there will be the line, instead of being like this, it will be flat and it will match the average. So in other words, the predicted values will be just the mean. So in a way, this is the sum of squares of when the situation is that there is no relationship between x and y. And we call this the total sum of squares. Now, the sum of squares of the regression line is where we'll take the deviations of each value, or rather each predicted value from the mean of all the observed values. We square them and sum them. And that's how we form the sum of squares of the regression. And this represents the amount of total variation that is explained by the regression model. In the case of simple regression, the sum of squares of the regression represents the amount of the variation that is explained by x, because we have a single predictor. All right, the next sum of squares is the sum of squares of the errors, the same that we've been talking about earlier on. And this is just the sum of the deviations of each value from the predicted value. So it's the sum of square of the residuals. And this represents the amount of the total variation that is not explained by the regression model. Or in the case of a simple regression model, the sum of squares of the error is the amount of total variation that is not explained by the single variable x in the model. All right, now that we have this sum of squares, we can define the R-square as the sum of squares of the regression divided by the total sum of squares. So by looking at that and how we broke down the sum of squares, you can see that the sum of squares total is equal to the sum of squares of the regression plus the sum of squares of the error. So given this summation and how that R-square is defined, then R-square is interpreted as the proportion of the total variation that is explained by the regression model. In simple regression, R-square is the proportion of total variation that is explained by the single X variable in the model. So again, when we talk about simple regression, we can blame everything on the single X. But when you have multiple regression, well, you have multiple X's and you don't know which one to blame for the impact on the R-square. But in simple regression, it's easy because we have a single X. All right, using this equality, so you can see that the sum of squares of the regression is just the total sum of squares minus the sum of squares of the error. And using that, we can calculate the R-square in this manner, or more appropriately for us, or better for us, because we have all the sum of squares and we have the estimate of the slope, we can calculate the R-square using the estimate of the slope times the sum of squares of the x-y products and the sum of squares of the y squares. So given what we've been calculating, this will be the best choice to calculate R-square. All right, now that we know this, what are the characteristics of this coefficient of determination? Well, number one, R-square can take values between 0 and 1. And the closer it is to 1, the larger the proportion of variation that is explained by the regression model. The smaller it is, in other words, the closer to 0 that this R-square is the smaller the amount of variation that is explained by the model. Now, I wanted to note that the textbook uses lowercase r-square. And if you were to look at the papers and books on regression analysis, everybody uses capital R-square. And I think the textbook uses lowercase r-square because it's relating it to the correlation coefficient that we'll discuss later on. All right, so I just wanted to make you aware that in the slides, I'm using capital R-square to designate the coefficient of determination. In the textbook, and as well as in the Wiley Plus assignments, you will see lowercase r-square, but it's the same quantity. All right, in terms of the 1 minus r-square, which is the proportion of variation not explained by the model, this could be due to two possible situations. Well, more than two, but I classify them into two. Number one is because your model is missing some important variables that have an important role in explaining the behavior of the dependent variable. So poor R-square may mean that the model is incomplete. You need to include other prediction variables. Another cause of a low R-square is excessive random variation in your data. So things are measured with not very precisely, and so you have a lot of variability, and that doesn't allow you to see how well the model represents the data. Another option or another case is that what you have is not random error, but rather systematic variation because you're using the wrong model. So the data may have curvature, and by using a straight line, now you have large deviations from some of the observations that are in the curve of the model from the straight line. So that could be another reason for a low R-square. All right, so let's go back to our example that we've been working with GPA and hours worked per week. So again, for this problem, we want to calculate the coefficient of determination and explain what it means. So again, from the different sum of squares that we calculated to find the estimate of the slope and the slope itself, then we can use this formula to calculate the R-square. In this case, the R-square is 0.46065. Typically, the R-square is described as a percentage. So we can say then that the variable hours worked per week, because this is the only variable in the model, explains only 46% of the total variation in the GPA data, which is not very good. You would like to have higher R-squares. So that means that the remaining variation, that 54% that is not explained by the model, is telling us that GPA depends on other variables, not just the hours that the student works per week. Maybe other things, maybe the health of the student, I don't know, other distractions that prevent you from studying, or other situations. So again, we're only considering a single variable, and this is indicating that perhaps we need to consider other variables in the model. Or maybe the data that we're using for this is not measured very precisely, which could be the case. Or maybe the GPA does not follow a straight line, or rather the dependency of GPA on the hours worked per week does not follow a straight line, maybe follow some sort of a curvature, and that those large deviations are resulting in a low R-square. We don't know. Later on, when we do the residual analysis, we may be able to provide a little more clarity on this. All right, so this is how you calculate the R-square and how you interpret it. I'm going to stop here, and then for next week, I'll start putting more slides for the other sections of this Module 11 and the corresponding recordings. All right.